Aluminium casting design guidelines. Casting design involves the specification of the overall configuration of the casting as well as the detailed geometry of the various features that comprise it. The goal of casting design is, first, satisfy the functionality and service requirements of the application. Second, specify a casting configuration and detailed design that results in low cost, high inherent quality, and short lead time. Design for strength and stiffness. The strength and stiffness of the casting will be maximized by locating material where it is needed. This figure illustrates the importance of metal distribution on the load-carrying capacity of a beam. All four sections have the same area and weight. The cross and round sections have only about 50% of the rigidity of the I-beam. Minimize casting weight. Weight of the casting can be reduced by designing the casting by utilizing a minimum uniform wall thickness everywhere in the casting. There are a variety of design approaches to use of thinner walls, for example, the use of ribs as shown in this figure. Design for uniform wall thickness. When heavy sections cannot be avoided, then risers or other costly foundry remedies must often be used. A far preferable approach is to avoid heavy sections by designing the casting to have a uniform wall thickness as it is shown in this figure. Avoid isolated hotspots and sharp internal corners. The corners of all intersections and junctions should have fillet radii. The size of the fillet radii used must often strike a balance between stress concentration and the possibility of a hotspot. The small filler radius inhibit the flow of molten metal during filling and also can cause cracking during cooling or use of the casting. If the fillet radius is made too large, isolated hotspots can occur because the metal mass at the intersection will be larger than the features that are joined. The casting designer should therefore specify corner radii that are neither too large or too small to ensure that both of these undesirable effects are avoided. Often, the best choice will depend on the particular alloy. For example, alloys that exhibit little solidification shrinkage are typically not sensitive to junction design, designed to avoid hot tears and distortion. As the casting solidifies and cools, it shrinks. If the mold walls and/or cores inhibit or constrain this shrinkage, internal stress will develop. This can result in hot tearing or cracking if the stress exceeds the strength of the alloy, or the stress may be frozen in as residual stress, causing distortion and warpage of the casting. Similar effects will occur if different sections of the casting cool at different rates, or if the distribution of metal is asymmetric. The best way to avoid hot tears and distortion is to avoid asymmetrical distributions of metal and to use a uniform wall thickness everywhere. When this is not possible, transitions to different section thickness should be carefully designed so that the degree of constraint imposed on the solidifying casting is minimized. Design for metal flow. Misruns and cold shuts occur when the molten metal solidifies prematurely in cross-sections that are too long and narrow or that are too thin. Alloys having poor or fair fluid life require thicker sections than those having good to excellent fluid life. Design for low foundry tooling cost. Every opportunity should be taken to minimize casting complexity and promote ease of fabrication. Design for heat treatment. Guidelines for achieving a heat treatment-friendly casting design are shown in this figure. When these guidelines cannot be followed, the designer is advised to consider the selection of an alloy that is suitable for lower temperature aging-only heat treatment or an alloy that is self-aging. Design for machining. Reduce the volume of material to be removed. Minimize the size of surfaces to be machined. Specify alloys and heat treatments that result in good machinability. Avoid tight tolerances. See more in the figure. Minimize the number of machining directions as it's shown in the figure. ensure access to surfaces that are to be machined, provide clearance for tool, specify features such as fillet radii that allow shorter toolpath lengths, use standardized features, avoid non-standard features, avoid sharp angles, edges, and corners. Thanks for watching. Remember to like, comment, and subscribe.